Hello. In this lesson, we'll discuss area calculation, specifically focusing on complex areas, not just those determined between the graphs of two functions. The objectives we are aiming to learn are these three that we see on the screen: applying the definite integral to compute complex areas, interpreting the results of the definite integral, and doing so thoughtfully rather than blindly. And finally, calculating complex areas, not just, as I have said before, between the graphs of two functions. What requirements do we need in order to move forward with this lesson? Well, we need to know how to calculate primitives, immediate primitives, and primitives of any possible function. The more we understand them, the better. The concept of the definite integral, which is the one that we are going to be using, and how to calculate the area enclosed between the graphs of two functions. This lesson is simply going to be focused on this example alone that we have here. We need to calculate the area of the region bounded by the lines x plus y equals 2, the line y equals 2, and the parabola y equals x squared. Specifically, the region that includes the points 0, 1. In order to calculate this area, we first need to determine precisely which region we want to study. To do that, on a Cartesian plane, we plot the graphs of the functions. In this case, first we have the line x plus y equals 2. Then the line y equals 2, which is the second one, and finally the parabola y equals x squared. It is essential that in the graph we draw, we get very clear cutting points. We have to see all the points where the different curves meet. In this case, we can see that all the cutting points between the different curves are shown in the graph, and that ensures that all the possible regions that determine the curves are visible. To calculate areas, we need regions that are bounded. Here, for example, we have 3 bounded regions and several other unbounded regions. The one at the top, the one at the bottom, and some on the left and right are unbounded. However, here we have 3 bounded regions indeed. The first one is highlighted right now, the second one, and the third one on the right. Those 3 are bounded. We only need to calculate the one that contains the point 0, 1. Let's see where such a point is located, and therefore what we are interested in is the calculation of the area of the highlighted region we can see on the screen. To calculate this area, we need to understand that we're working with a region determined by the graphs. The lower boundary is always the same function, x squared, but the upper boundary changes. In one section, the upper boundary is the function y equals 2, and in another section, it's the graph of x plus y equals 2. That forces us to divide our process of integrating into 2 different regions. Firstly, in order to calculate area A, we first calculate region A1 and then region A2. The main area will be the sum of those 2 areas. What are the great news about these 2 areas? Well, these 2 are exactly the regions determined between 2 graphs, and therefore the process is very straightforward. Let's get started by calculating A1. The first thing we need to find is the projections of the intersection points. Here we can see the 2 intersection points. We project them downwards and realize that the first one is minus the square root of 2, and the second one is 0. Therefore, our integral will be, as we can see, minus the square root of 2, 0. And now, in the integrand, we will include the upper function, which in this case is y equals 2, and the lower function, which in this case is x squared. As we have seen, we should start from top to bottom, taking the entry point first, which in this case would be y equals 2, and later the exit point, which would be y equals x squared. Similarly, in the second region, we go back to look for the cutting points of the projection, and we find out that they are 0 and 1. Therefore, our integral would then be between 0 and 1, and again now the graph above would be 2 minus x, and the graph through which we leave, in other words the bottom one, would be x squared. These remaining integrals are very simple, they are polynomial, and the primitive calculation gives us an immediate primitive, and therefore the calculation is straightforward. The total area would be the sum of these 2 areas. The first 4 divided by 3 of the root of 2, the second one 7 divided by 6, and by simplifying we obtain the final result, 8 multiplied by the root of 2 plus 7 divided by 6. Well, this is the calculation for today. After this lesson, we should know how to calculate more complex areas through the defined integral, and to properly interpret the results of such defined integral, which is normally done by interpreting each one of the calculations. That is all, students. Thanks for your attention.